The last part of this chapter on water involves looking at water pollution, and also involves looking at ways in which we can measure the levels of pollution in a given body of water. And finally then, the very last part will look at how we measure what's called free chlorine in a sample of water. Now, the reason why we look at free chlorine is because we're all very conscious that in public swimming pools there has to be a continuous disinfectant, and disinfecting of the water is carried out by chlorine. So we'll talk about that at the very end. Anyway, what is water pollution? First of all, water pollution is a way of reducing the quality of a body of water. That's it. Anything we do to reduce its quality is polluting that particular water. And we look at it as biologists and as chemists, we look at it in relation to how the pollution affects life within a body of water. So as it says here, one of the ways that pollutants affect the quality of a body of water is by reducing the amount of dissolved O2 available to aquatic life. If you remove the oxygen from a body of water, anything dependent on that is living will simply die. So you have fish, you've got smaller animals, you've got plants, they're all looking for this supply of oxygen that's in the water, and it is very, very sparing, it's very, very small, it's just enough to keep them alive. But if we reduce that, then we'll obviously have an impact on the life within that body of water, and it will cause death, and it will cause decay, and it will cause eventually what we call eutrophication. Now, eutrophication is the process by which we deplete a body of water of its oxygen content, which leads to the death of animals and plants in there. But you might ask yourself, well, how do we decrease the oxygen supply? How does the oxygen supply get depleted? And the answer is linking back to what we talked about, the sewage treatment scheme. If we allow nitrates and phosphates into a body of water, they, as far as the algae are concerned, which are tiny microscopic plants, green plants, they are their favorite food. They will feast on this stuff. They will multiply rapidly. And as they multiply rapidly, they will simply take over the surface of a body of water. They will cover the body of water with a blanket of algae, cutting off the sunlight, stopping photosynthesis, causing death in plants, causing decomposition, causing usage of oxygen, causing a depletion of oxygen, causing animal life to die. So it is quite a set of dominoes, which begins with what we call the nitrates, the NO3s, and the phosphates, the PO4 radicals we spoke about in fifth year when we were doing the anion tests. So the enrichment of water with nutrients, nitrates and phosphates, that's where it all begins. Okay, so when we talk about eutrophication, this is where it starts. So if the water that's coming from a sewage treatment plant hasn't got treated for nitrates and phosphates, they will escape into a body of natural water, they will feed the algae, and then the domino effect will begin, which will lead ultimately to the depletion of aquatic life. They enter the water supply from sewage, from silage, or from milk spillage, as well as industrial waste. Now, farmers know when they're dealing with silage, they have to be very, very careful, because a spillage of silage or an escape of silage from the farm into a river or into a natural supply of water brings with it huge fines. They get into serious trouble if there's silage or sewage getting into a natural water supply. Indeed, milk spillage as well, because milk is organic, it does the same thing. When they enter the water supply, they cause an algal bloom, and the bloom cuts off the sunlight, stops photosynthesis in bed plants, they die, they decompose, they cause aerobic bacteria then to go and use the dissolved oxygen, which means the oxygen will be used up and the animal life will then suffer. So eventually causes animal death and further decomposition. I don't know whether you've ever come across a stagnant body of water. Poke the surface, get the smell. You'll understand eutrophication if you smell it. You'll never forget it. So this is just a small diagram to show you exactly what goes on with eutrophication, where it all begins. So here's your farm. Animals, obviously. You'll have nitrates from their excrement. You will also have fertilizers being used on the soil to give us good plants. But all of this falls into what we call the natural fresh water. Bacteria then in the ground, when this gets into the ground, the bacteria in the ground will turn the nitrogen contents into nitrates. They will then further come down here into the groundwater, and the groundwater then will obviously go down to a freshwater system where we have animals and plants in balance. That's the key thing, they're always in balance. But if you give them nitrates, they think it's Christmas, and these guys here go to town on this. They will eat it, they will grow, they will multiply rapidly, and eventually the algae will take over that body of water. They will cause death of plants in the bottom. They will cause a drop in the O2 content here, so the O2 levels will drop, and then the fish and other animals that depend on that oxygen will simply die. We also have another source of pollution, which are heavy metals. We spoke about this again when we were dealing with the sewage treatment scheme. When we notice that water contains heavy metal ions, metals for example like lead, like mercury and so on, and of course cadmium, which is a big one from batteries, they have to be removed. And the way in which they're removed is by what we would say precipitation reactions. So we add in chemicals, and these chemicals, aluminium sulfate is usually one of them, it will take these lead, these mercury and these cadmium salts or metals out into salt complexes and take them out of the water. So it's a precipitation reaction. These three metals by themselves, mercury, lead and cadmium, in very tiny doses, harmless, but they build up in the body. If we consume them, or if they get into our system, we've no way of getting rid of them. So they build up small bits by small bits until they get to what we call a toxic level. And then once we reach a toxic level, the effects of those metals becomes quite visible. Birth defects, depression, and eventually death if the levels get very, very high. So it is urgent that these things are removed from the water before it's discharged back into the supply, the natural supply. They're removed by precipitation reactions, and usually again aluminium sulfate. It's a great thing. Aluminium sulfate, Al2SO4 3 times. So that's your aluminium sulfate, which was also used as a flocculating agent when we were dealing with the water treatment, correct? And that pulled little particles together and brought them out of water. So what's the BOD? Well, it's the biochemical oxygen demand. Now listen to the words again. It's the biochemical oxygen demand. And what that means is, read it backwards, it's the demand that is made on the oxygen in a body of water by the biological or chemical systems that are in that body of water. That's exactly what it means. Now we can break it down into BOD. That's what it's actually called, the BOD. So we have a BOD test, which is the biochemical oxygen demand test. Pollutants create a demand for the dissolved oxygen in water, and this is known as the biochemical oxygen demand, or the BOD. It is measured by calculating the amount of oxygen consumed by a biological action when a sample of water is kept, you notice in red, darkness, for 5 days at 20 degrees Celsius. Now those three conditions are extremely important. If you're going to measure the BOD of a sample of water, you've got to make sure that when you get your body of water, you split it in half. The second half is put into darkness for 5 days at 20 degrees. The first half is basically titrated immediately to work out the oxygen concentration at that stage. So normally what we do is we take a body of water, split it in two, put one away for 5 days in darkness at 20 degrees, take the first sample, we experiment on it there and then by the Winkler method, which we'll talk about in a moment. That reveals the amount of oxygen present in that body of water. Now, then after 5 days we come back, we do the titration again on the second body of water, and we see how the oxygen content has changed. Has it decreased? Has it decreased by a little? Has it decreased by a lot? And the amount of oxygen that is lost or used up or consumed is also a measurement of the pollution of that particular water. So the more oxygen that's lost over those 5 days, the more polluted that water sample is. So why darkness? Well, obviously those biologists amongst us will know that darkness cuts off photosynthesis. So if we're going to have a body of water that we want to test the oxygen levels of, we can't have microscopic plants replacing the oxygen that's being used up. So we put it into darkness to stop the photosynthesis, to keep the oxygen levels where they are. Why 5 days? Well, we've discovered that that is sufficient time to give us a good reading. It'll let us see exactly what the demand of oxygen is in that water supply. If we went before, the supply, the water supply or the oxygen supply mightn't be decreased enough. If we left it too long, it could be deficient of oxygen completely. So they've discovered that 5 days is the best time period for this particular experiment. And then why 20 degrees? Standard room temperature. Don't need a fridge, you don't need an oven, you just put it in a dark place for 5 days at normal room temperature. Okay, so what is the Winkler method? Now, the Winkler method is a titration. Alright, so this is your last titration. Unfortunately, we're not going to get it done unless we go back to school maybe before the Leaving Cert exams, but it's a titration method in which the amount of dissolved oxygen in a water sample can be measured. Very, very small quantities of very concentrated chemicals are used. Now I'll talk about this in a second slide, but that's extremely important because the water is what you're dealing with. The water is what you're analysing. So we don't want to have too much chemical added in. We need tiny amounts of very, very concentrated chemicals, which means that tiny volumes pack a lot of chemical in there. Okay, we don't be putting in large volumes that'll displace a lot of water. So tiny volumes of concentrated chemicals deliver a lot of chemical, enough to do the job quite well. On addition of concentrated H2SO4 towards the end of this particular first step, a reddish brown solution of iodine appears. Now we've done titrations with iodine before, if you remember. Yeah, sodium thiosulfate and iodine, exactly. Those two were used in a previous chapter when we were looking at redox reactions and redox titrations. Now we're going to be using the same thing again, but this time we're going to be looking at the iodine, revealing to us by two steps the concentration of oxygen in a body of water. So let's begin. What is the Winkler method? Well, step number one is that we take a body of water. Now you'll notice it's filled to the brim. Okay, this is one body of water in a little reagent bottle, and it's filled to the brim. And the reason why we fill it to the brim is so that there's no air trapped when you put the lid back on, that you don't have any air containing the usual 20% or 21% oxygen that could get into the water and then bring the levels of oxygen back up again. So we fill it up to the brim and we keep the lid on in between the additions of chemicals. And there are three steps in here. So that's the first thing. First of all is it's filled to the brim. We've got to remember that. Now, the three chemicals we have to add in, notice where they're added. They're added down into the body of the water here. And there are two reasons for that. Again, number one, we don't want to be introducing air into this sample because that's what we're measuring. And air contains 20% oxygen. So we don't want to be adding air in here. We want to make sure that what we deliver is the chemical and the chemical alone. And secondly, because we're delivering very concentrated chemicals, they don't sink very well. What would happen is if we were to put them up here, they'd run off the top. So if we were just to drop them in, they'd run off and they wouldn't get in. So we put them down here into the body of water to make sure that they mix well and that they don't escape. Okay, so they're the two reasons why the pipettes are placed underneath. So what are the three reagents? Well, into the first bottle we put in very concentrated manganese sulfate. Now when you add in the manganese sulfate in the first one, number one, we don't see any noticeable change in the body of water. The second chemical we add in is what we call alkaline potassium iodide. Alkaline is the NaOH, but it's alkaline potassium iodide, and again it's extremely concentrated. And this time we're hoping that we're going to notice a change. So when the second chemical goes in, we're looking for a brown, kind of a cloudy precipitate. Now at this stage, if we get a brown cloudy precipitate, happy days. That means that there's oxygen in your body of water. If the addition of the alkaline potassium iodide gives a white precipitate, that's telling you there's no oxygen in that water at all, so you're wasting your time. Okay, so we're looking for a brown precipitate. We don't want a white one because the white one tells us that there's no oxygen present. Finally, after we've added in those two, the third one to be added in is concentrated sulfuric acid. Now, when we add in the concentrated sulfuric acid, this will release the I minuses, ions, and they will come together as I2. So this is where we release the free iodine, and it's the iodine that is going to go into my titration. Okay, so they're the three chemicals. Concentrated manganese sulfate, no change. Concentrated alkaline potassium iodide, we're looking for a brown cloudy precipitate. And finally, on the addition of 1 centimeter cubed or less of concentrated sulfuric acid, it will turn from that brown cloud into a beautiful dark reddish brown solution of iodine. And finally then, as we said already, why do we use concentrated chemicals? We use concentrated chemicals because they deliver a lot of chemical in a very small volume. So we're not displacing too much water by the addition of these chemicals. Once that's done, and once you've got your bottle of iodine, you've actually trapped your oxygen. So therefore, because you've now trapped the level of oxygen in there, we can titrate this bottle, the solution, the iodine solution, against sodium thiosulfate in the same way that we titrated them when we were doing redox reactions. So the procedure for a titration is followed. You'll notice that when we allow in the sodium thiosulfate into the iodine solution, it'll go a pale yellow colour. At this stage, we must add in starch indicator. The starch indicator will take the yellow to a dark blue-black colour, and then we titrate again until we get a colourless solution. So you'll remember that from doing it in class when we're doing redox reactions. Just keep in mind, we always do titrations times 3. We ignore the first reading, and then from the second one and the third one we get the average. So ignore the first, and then you get the average of those two. You know that already because you've done plenty of these before. Okay, so let's just finally then take a look at some of the important points. The actual titration itself that's used is between sodium thiosulfate and the free iodine in the water sample. This is an equation you already had before, and it's an equation that we will need to look at in relation to the other chemical equations that are going on in the body of water. But what you'll notice here is that there is a 2-to-1 relationship between the thiosulfate and the iodine, and that's important. Okay, there's a 2-to-1 relationship between the iodine and the thiosulfate. So we do that again, 2:1, and we'll need that in order to get into our titration in a few moments. Remember to titrate to pale yellow, add your starch indicator, and then continue to titrate until the blue-black colour turns colourless. So there are 3 equations that we need to remember, and I'm going to spend a while on these. So there is your what we call manganese hydroxide, which will bond with the oxygen present and give you manganese oxide and water. Secondly, the manganese oxide that's then formed will react with the iodide ions that you've introduced in the alkaline potassium iodide in the presence of acid, and they will become manganese ions and free iodine. So this is where we get that lovely red colour coming from in the reagent bottle. Then the iodine is titrated in the usual manner against the sodium thiosulfate to give you back colourless iodide ions, and then the rest of those ions that we don't bother about, they'll just float around in the water by themselves. Now what's important here, and what I want you to look at, I'm going to change colour for this, is I want you to just take a look at what's happening in relation to the ratios. Notice the link. Manganese oxide, okay, iodine and iodine. So if we were to try and take these 3 equations as one continuous equation, here's what we'd have to do. Notice the link is here, okay? So if this ends in 2Mn2O3, that would have to start in 2MnO3. So I want to multiply everything here by 2, which will give me 4 of those, 12 of those, 4 of those, 2 of those, and 6 of those. Okay, now the link between these two is the iodine. So if you finish with 2 iodines here, you have to start with 2 iodines there, which means I've got to multiply this whole line by 2 to give me 4 of them, to give me 4 of them, and 2 of them. Now what am I interested in? Here's what I'm interested in. 1 oxygen reacts with 2I2, which in turn with 4S2O3. So we actually end up with a 1:2:4 ratio between the oxygen and the iodine and the thiosulfate. And that's extremely important for your titration, because from these 3 numbers here will come your N1 and your N2, depending on what you're going to use in your titrations. You can use the thiosulfate versus the iodine. You can also use the thiosulfate versus the oxygen. That's up to yourself. I'll go through a few questions. You can decide what's easiest for you to do. But that's the importance of those reactions. Okay. Now, as I said already, so let me get rid of that there. Text in the way. Get rid of all this. This is printed there for you. There you have it. It gives a 1:2:4 relationship between your oxygen, your iodine, and your thiosulfate. Okay, small quantities of concentrated solutions, we know this, they're added, so a lot of chemical can be added in a tiny volume, that's fine. The chemicals are added under the surface of the water so that they sink, they fully react, and they don't spill out over the top of the bottle. Anything I've placed on these slides twice is extremely important, so therefore that's things you do need to know and things you do need to remember. There is a video here, you can look at that video yourselves, and that video will bring you through the entire Winkler titration experiment that unfortunately yet we can't do, but it's the only titration we have left to do, so if we get a chance we will do it. But do take a moment, take a look at that video and make sure you understand the steps within. So let's take a question. This is the most important thing. A 100 sample of water, 100 centimeter sample of water was analysed by the Winkler method, and the iodine released was found to require 4.8 centimeters cubed of a 0.02 molar solution of Na2S2O3 for titration. Calculate the concentration of dissolved oxygen in the water sample. Okay, what are we doing? what are we titrating? We're titrating the iodine released versus the sodium thiosulfate. So therefore we're looking at iodine and Na2S2O3. They're the two things I'm going to titrate. So as always, you know it's a titration. V1, M1, N1, V2, M2 and N2. Okay. And everything except the concentration of iodine will be given. So how much iodine? 100 centimeter sample of water was analysed by the Winkler method, and the iodine, so 100 centimeters cubed. Okay, 4.8 centimeters cubed of thiosulfate is V2, and the molarity of the thiosulfate is 0.02. Now, what's my N1 and N2? Look at the two things that you're using, iodine and thiosulfate. So iodine and thiosulfate from here, you'll notice, is a 2 to 4, better known as a 1 to 2 relationship. So the iodine gets a 1 and the thiosulfate gets a 2. And off you go. 100x is equal to 4.8 by 0.02 all over 2, which is 200x equals 4.8. Get my calculator. So 4.8 by 0.02 comes out as 0.096. 0.096, and then if I divide both sides by 200 to get x, I get an answer of x equals 4.8 by 10 to the power of minus 4 moles per litre of iodine. Be careful, it's iodine. Okay, now if I want to go back and figure out, well, how much oxygen does that represent? Go back to the ratio. Yeah, there's a 1 to 2 relationship between iodine and thiosulfate, but look, there's a 1 to 2 relationship between the oxygen and the iodine. So therefore, if you're going from iodine to oxygen, you're halving. See that? So therefore, I2 to O2 is a 2 to 1 relationship, which means I'm going to divide that by 2. And if I divide that by 2, and do it again. So 4.8, I get 12. That's easy, you shouldn't even need a calculator for that one. 2.4 by 10 to the power of minus 4 moles per litre of oxygen. Now, you don't give your concentration back like that. Because this is a biochemical process, because it's environmental chemistry, you always give your concentrations back in parts per million. So therefore, let me just take it up here. So 2.4 by 10 to the power of minus 4 moles per litre. What do I want to go to? Well, let me just do that as a separate section. I want to go to ppm, parts per million. So the first thing I've got to do, remember the parts per million is milligrams per litre. So the very first thing I'm going to do here is go to grams per litre through multiplication by the mass of oxygen, because it's oxygen we're looking at, which is O2, which is 32. So 2.4 by 10 to the power of minus 4 multiplied by 32 comes out as 7.68 by 10 to the power of minus 3 grams per litre. That's grams per litre. I want to go to parts per million. Now I've got to multiply by 1,000 so that I can go to milligrams per litre. And if I multiply that by 1,000, I get 7.68 milligrams per litre, which is 7.68 parts per million, which would tell me that the water isn't heavily polluted at all. There's only a demand, this is the key thing, there's only a demand of, there's only a presence of 7.68 parts per million of oxygen in that water supply. Now, that's very little oxygen. 7.68 is very, very little oxygen. But what we don't know is, what's the demand? What is the demand for this thing? Because we have nothing to compare it to. So that's just how you calculate the composition of water, or the concentration of water in that particular sample. Okay, I'm going to finish this now very quickly, and I'll do another exam question in a few minutes and in relation to the Winkler method, but I want to just take a look at the last section, the very last section, which is easy enough. The instrumental methods that are used in the, I suppose, the chemical analysis of water. What are we looking for? Is it pH? What are we looking for? Is it heavy metals? What are we looking for? Is it free chlorine? Is it oxygen, etc.? So we already know that if you want to get the amount of calcium in water, you carry out the calcium test with the EDTA. We did that already in class. If you want to get the amount of oxygen, it's the Winkler method. These three are often examined as well. You've got, how do I get the pH? How do I work out the concentration of the heavy metals like lead and cadmium and mercury? And how do I work out the free chlorine content in a body of, say, swimming pool water, for example? So if I want to take a look at the pH, obviously you're going to use a pH meter. Universal indicator, of course you could use a universal indicator as well. A pH meter is probably less invasive. You're not adding chemicals to the water, you're just using a probe. The probe goes in, it gives you the pH on a screen, you write it down. If we're looking for the heavy metals of cadmium, mercury or lead, the best thing to do there would be atomic absorption spectroscopy. Do you remember the line spectra? Exactly the same thing. You could use the flame test for their presence. You could also use, I suppose, the mass spectrometer in order to work out their isotopes and so on. But the atomic absorption spectrum would tell you the elements that are present by giving you their fingerprints in a line, what we would call a line absorption spectrum, where because it's absorption, you'll have a coloured background with black lines on it. Again, revise that as you're going over the earlier chapters. And lastly then, what we're going to look at in this section is the analysis of water for the presence of free chlorine, and we do that by a process called colorimetry. And as the name suggests, yes, colours. You're looking at colours. We're going to use a unique way of a comparator, which is a little small black box, and a little small black box has two compartments. The compartment A contains the body of water without any DPD tablet in it. The second part contains the little vial with the DPD tablet in it. Now what you'll notice is you take into your little vial, and I'll show you in a second, you take into your little vial a sample of your water, you add in what's called a DPD tablet and you crush it. If there is chlorine present, the water will turn a shade of purple, and the shade of purple is directly linked to the concentration of chlorine. Okay, so as we said here in this slide, a sample of water under test is placed into a small plastic vial. Now that just means it's like a small little box like that, very, very long, and you just put it in there. There's your water, like that. So it's kind of like that. And you put your water in and your little sample, and you put your little tablet there and you crush it. That's called your DPD tablet. Okay, so a DPD, and you do have to remember that, you don't have to know what DPD stands for, but you do have to understand that it is DPD, it's the chemical that reacts with the free chlorine. It's added to the sample of water, it's crushed, it doesn't dissolve by itself, it's crushed, and it turns a kind of a shade of pink. Now, the shade is what's important. So, the vial is placed into a comparator, that's the little box I'll show you in a moment, which contains a disc of varying shades of pink. The disc is simply rotated, so it's like one of those things you used to have as kids, you know, you used to look up and the thing would spin. Very similar to that, except you move the little wheel until the purple colour on the disc that's present matches the purple colour that is inside your little vial that you crushed the DPD tablet in a few moments ago. So the disc is rotated until the colour of the water matches the colour on the disc, and the disc reveals directly the concentration of chlorine. Again, there's a video that'll bring you through that process. Make sure you look at that video, see how they use the comparator, and that's what we're going. There's two ways to do it. You can do it electronically, or you can do it by the comparator. We have a comparator in the lab, so we always use the comparator. So there's only need for you to talk about the comparator when you're actually giving back your answers. Okay, so what is free chlorine? This is something they've asked a couple of times. What's free chlorine? But think about the name. It's the chlorine that is free to attack the pathogens. Okay, so free chlorine is the chlorine that's available to combine with contaminants in the water to disinfect and sanitize the water. So for example, if you have a body of water with these little pathogens here, it's only the free chlorine, see those bubbles? It's only that free chlorine that can actually attack those and kill them, and therefore sterilize or disinfect a body of water. Chlorine that is added to the swimming pool is free chlorine, in that it has not yet bonded with nitrates or ammonia or other compounds in the dirty pool water. So free means free, it means available. It's chlorine that's available to tackle the pathogens or any other things in the water that will actually pollute that body of water. So there it is, there's your comparator. Now, we call the process colorimetry, we call the object the comparator. A-R-A-T-O-R. Okay, you can see it down there, kind of in handwriting, the comparator. do that again, comparator, which compares, that's where the name comes from, it compares the colour of purple that you get in the little file to the colour of purple that is on the disc. So that colour there is matched up to the disc through the addition of what we call DPD tablets. So let's take a look at these questions here. I'm going to run through a few questions just to make sure that we pull the whole thing together and that we've left no stone unturned. Unfortunately, the practical work itself, but please God, we'll get that done when we get back to school. So, past exam question here from 2016, question 9. To determine the biochemical oxygen demand of water in a lake, 2 samples were taken and 1 was tested immediately. Under what conditions was the second sample stored? Now remember, when you're going to analyse a body of water for the biochemical oxygen demand, you take the sample, you break it in 2. One you analyse by the Winkler method immediately. The second one you leave in darkness. For how long? Yeah, 5 days. I can really hear you, I can. For 5 days, at what temperature? 20 degrees Celsius. They're the 3 conditions. And then it says, what time interval was it tested? Well, after 5 days. After the 5 days are over, that's when we do the second test. And we carry out the Winkler method again. And what we do is we look at the original amount of dissolved oxygen. We look at the amount of dissolved oxygen after 5 days. And the bigger the depletion, the greater the pollution in that particular water. The result of the BOD test suggested that eutrophication had occurred in the lake. Define eutrophication. Now, there are 2 things I want you to remember about eutrophication. First of all, it's the enrichment of a body of water with nitrates and phosphates. Okay, that's what you got to remember. It's the enrichment of water with nitrates and phosphates. What happens? That leads to an algal bloom. What does that do? That stops photosynthesis. Okay, what does that do? That causes death in plants and decomposition. And what does that do? That gets the aerobic bacteria going, which eventually deplete the O2 content in the body of water, and that causes death in animals. Now, that's just me going through all that again for you. But if they want you to define eutrophication, it's the enrichment of water with nitrates or phosphates leading to an algal bloom and eventually to a decrease in the amount of dissolved oxygen. It says here, suggest a state one of its harmful effects. Well, we've had loads. It stops photosynthesis. The plants that can't photosynthesize die. The aerobic bacteria take over and they go into decomposition, and the decomposition uses up oxygen, which results in the death of animals. Suggest a possible cause of eutrophication. There's loads. You can have sewage spillage. You could have milk spillage. You can have silage. Or, from our own houses, the nitrates and the phosphates. They're the ones that do the damage. Why is there concern about lead? Well, lead, as we already know, in drinking water is toxic. It's a very toxic metal, okay? In small, tiny quantities, it's okay, body can kind of tolerate it, but once it gets to a critical level, then we start to see the harmful effects. Name an instrumental method that could be used to analyze water for heavy metals. Atomic absorption spectroscopy, we had it already. Absorption. Now just remember, absorption, that means that it has a coloured black background with black lines, okay? So atomic absorption spectroscopy. S-P-E-C-C-O-P-Y. Okay. How can lead be removed from a contaminated water supply? No chemical reactions needed. The only thing you've got to say there, lead, whether it's Pb, whether it's cadmium, whether it's mercury, doesn't make any difference. They're the toxic ones. We take them out of a body of water by precipitation reactions. You don't have to know what the reactions are, but we did say to you aluminium sulfate. That's usually what takes them out. Okay, it is used as one of these reagents to pull these heavy metals out of water. And lastly then, how does temporary hardness arise in a rainwater flowing over from limestone? And it says write a balanced equation to describe the formation of lime scale when this water is boiled. So how does temporary hardness arise in rainwater flowing over limestone? Remember, let's do it over here. We've got the cloud, yeah, H2O. We've got the CO2, both of those combine into H2CO3, which is naturally acidic rainwater. It's called carbonic acid. That then flows over the calcium carbonate, which is the limestone, the CaCO3, and the two of those combine into CaHCO3 twice, which is calcium hydrogen carbonate, which is soluble. And that's what gets into our water supply. That gets dissolved in the water and carried away then into domestic water supplies if it's not treated before it gets to the domestic water supply. Part 1. Write a balanced equation to describe the formation of lime scale when this water is boiled. Now when you boil water, you undo the natural process. So the calcium hydrogen carbonate, yeah, the CaHCO3 twice, when that's heated, it simply decomposes into the carbon dioxide, the rainwater, and the calcium carbonate that came from the limestone region. And this is what we call lime scale. Okay, explain in words or by a balanced equation how this water with temporary hardness is deionized. Now, it's important that you're dealing with temporary hardness. Okay, so because we're dealing with temporary hardness, we're dealing with calcium hydrogen carbonate. Okay, and that's important because that's what causes the hydrogen carbonates with the calcium and magnesium that causes temporary hardness. And we know when we heat that, basically we can get rid of it. But also it says here, how does this water with temporary hardness, how is it deionized? Well, first of all, you have one bead of resin over here with H pluses. You've got another bead of resin over here with OH minuses. Now, the Ca2 plus from this water attaches to the bead and sends out 2 H pluses. The HCO3 minus will attach to that and send out 1 OH minus. So another one comes along here, attaches there and sends out another OH minus. So you can see immediately what's going to happen. These two will get together and form H2O, and then these two will get together and form H2O. And the water becomes completely deionized. What was water with calcium and hydrogen carbonate ions is now water with no ions whatsoever,